Okay, everybody is welcome to attend, I'm sure, what will be a beautiful lecture by Professor Jens Eggers from University of Bristol, who will give us a beautiful talk, I'm sure, on geometrical singularities and free surface cusps. And I see also a book advertised there. Jens, to you.
Yeah, thank you very much for the kind introduction, Renzo. Hello, everybody. I'm very pleased that you highlight our book, which is here on the front page. So, what has fascinated me about cusp singularities on free surfaces for quite some time is their geometrical underpinning, and it's because of this geometrical underpinning is that they are describing an unusually wide variety of problems, giving very similar answers. And here is a brief overview. Mainly today I'll be talking about the cusp or near cusp singularities on the free surface of a viscous liquid. Here you see a home experiment that's very easy to do. You take some olive oil, you pour the olive oil into a container, and if the speed of impact is sufficiently high, the free surface of the bath gets deformed into something that almost ends at a point, then returns here and merges back with the impacting jet. So this is strictly speaking a three-dimensional problem, but essentially this here is a knife edge that's wrapped around the jet. So for all intents and purposes, it is a two-dimensional object, and almost all I'm going to say today is within the realm of two dimensions. You got very similar cusp-like singularities in elasticity, like the cuspoidal end here on the border of a slice of bread. And remarkably, this is yet a completely different cusp, namely a cusp caustic. Caustics are these lines of very high intensity when light is focused in a natural way. And the most prominent singularity, the most prominent caustic one finds is this line here, which again ends in a cusp. And this similarity extends to quantitative answers. In all of these cases, if I measure the width of the cusp here as a function of the distance from the tip of the cusp, I'll see a characteristic exponent r to the 3/2. However, one should be aware that this universality does not apply to all cusps. For example, if I have two spheres that touch and ultimately emerge in the far field of the solution, you also have a cusp, but simply by the geometry of having two round objects, this is a width of r to the 1/2 here. R squared, of course, r squared, which cannot be of the same universality class as the cusps I mentioned on the earlier slides. It's also important to distinguish from three dimensions. This is another kind of problem on which I've done quite a bit of work recently. It's essentially, or in most of its manifestations, something that goes to back to G.I. Taylor. You take a low viscosity drop or bubble inside a flow, and again, if the flow is strong enough, the tip of the bubble is deformed into a sharp object, but this time the object is close to a cone with, as it turns out, from a much more detailed calculation with logarithmic corrections. And again, there are all sorts of nice manifestations of such cones in 3 dimensions, but which are in an essential way different from the 2-dimensional cusp. To mention an important application of these viscous free surface cusps in particular, these cusps to my mind are extraordinary importance because they serve as the entryways of another phase, typically air, into a liquid. So if you beat an egg, you shear the fluid, and in response to the shearing, the surface becomes deformed into a near cusp, and it can be shown and that owing to the sharpness of the cusp, a high pressure develops inside the cusp and air is forced into the liquid, which is a natural way to produce air entrainment. There is a sister problem to this, which you can very easily observe if you go hiking in the mountains. And again, you see empirically that it's very easy in such a situation to entrain air, yet this is an unsolved problem. No one has worked out how this mechanism would work in a situation where viscosity is negligible or almost negligible. But let me come to the idea of why geometry might unify the description of very different systems. Let me give you an example of a fold. So imagine I have a function, h of x. The only thing I'm requiring is that the surface is nice and smooth. Now I imagine this is like a sheet of paper or a blanket, and I have something smooth, and I simply push one end so that it folds over. So if I have this, then there are two special points here, fold points, and the only requirement for that set the properties of these fold points is that the original curve was smooth, and I'm deforming this curve again in a smooth way. Say parameterized by some parameter which I call t, as in time. So it's clear from this geometrical construction that the shape of the interface near this point must be x minus some shift equals some amplitude times h minus h0, where h0 is this point here squared. So quite naturally, again, using smoothness of the curves and deformations involved, I find a universal scaling exponent 2, which describes the shape of this fold. Now, let me ask, where did this fold come from? So I want to rewind, and I want to try the point in between this situation and this situation where this fold first appeared. And it's clear that this place where the fold first appeared must be one where, in fact, the interface has just become vertical, which means that up to shifts, x goes like a times h cubed. And again, in this situation, there is some universal exponent that governs the transition from no fold to having a fold. But once I've done this, I can expand around this point here, and I can ask, what is if I perturb this situation slightly? And I simply take the most general perturbation that is consistent with smoothness. And in my expansion, so I allow, this was the original term, and now I allow perturbations proportional to h, and perturbations proportional to h squared. I don't take into account perturbations of order h to the fourth, simply because near this point h is going to be small, so the any perturbation of higher order in h will be small. So to leading order, any perturbation I might introduce will be of this form. And it's easy to see that simply by a shift in h, I can always eliminate the quadratic term here, and I end up with a universal family of curves which describe the transition from a unfolded smooth curve to something that has been folded over. And in any such situation, the folding will be described by this law here, where t is a parameter, such that for t equals 0, I have the unfolded state, and for t greater than 0, the folded state. The only assumptions, but crucial assumptions I've made, is that everything is smooth. The original curve is smooth, and deformations I'm introducing are all smooth. And that might not always be the case. In fact, in the example I gave of two drops touching, I introduce a very singular point with the two drops touching, and there the assumption of smoothness is not valid. And that's the reason why I get a different type of solution for this problem. But now I can also ask, as t varies, where is the location of the fold? So the location of this object here, obviously, is where I have a vertical slope. So dx dh is 0. So that allows me to write hc, this point here, as a function of t. I insert back into the original expression for x, and I find that x goes like hc to the third. So indeed, the formation of such an turning over of the profile, simply making the assumptions that all the deformations are smooth, is described by a universal structure, which is a cusp. So xc, the position of the fold, as function of t, of the parameter of deformation, is automatically like t to the 3/2. And experts will know that this is precisely the reason. This is essentially the derivation of the cusp seen in the caustic picture. This is the reason in caustics always have this characteristic shape, because these places here where the interface is vertical is one where the light is amplified. Okay. So this is a very simple example how I can make mileage out of these simple geometrical transformations. So let's try to apply it. Again, of course, the cuspic stone is 3/2, as we've seen before in the pictures. Let me try to relate it to viscous flow, because that's the actual physical problem under study. So in a first attempt, let's look at a possible cusp and look at it from a coarse-grained perspective. So crucially, what I'm neglecting here is the inner structure of the cusp tip here. And if I do that, then since this is a slender structure, in particular since the width of this cusp here is small compared to the height, I imagine that I can, from a coarse-grained perspective, describe this situation like a crack in a viscous fluid. So I have a line here that ends at the cusp tip and along which there is no stress. But other than that, I'm solving Stokes' equation, and the experts will know that if I describe two-dimensional flow using a stream function psi, then the Stokes equation is equivalent to the Laplacian squared of the stream function being equal to 0. And once I've solved this equation, I can then deduce what the original velocity field had been. And the trick is to use scale invariance. So this picture here on the right-hand side doesn't have a characteristic scale because the thickness of my gap here is arbitrarily thin. So it's natural to look for a similarity solution of the form r to the alpha, where alpha is some unknown exponent, times a scaling function f of the dimensionless angle phi here. And I don't want to go into the details of the calculation, but it's quite straightforward. What you do is you insert this here into this equation. You find the solution, which turns out to be a simple function in terms of sines and cosines, and then you impose the condition that there is no flux across this crack here and zero stress. And this will lead to a solvability condition, namely a condition that in order to have a non-trivial solution, so a solution where there is some flow at all, alpha has to satisfy an equation which you can solve. And owing to the periodicity of the sines and cosines, this is a sequence of alphas, the lowest of which are 1, 3/2, 2, and so on and so forth. And you're interested in the smallest value of alpha. Why? Because for small r near the local solution, this will dominate. So the first solution is alpha equals 1. Well, alpha equals 1 actually corresponds to a trivial solution, namely to a uniform flow in the direction of y. That obviously satisfies immediately all boundary conditions. So, but apart from this solution, which we're also interested in, the next one then, the first non-trivial one, indeed has this exponent 3/2. So let's try to work out what this means in terms of the shape of the cusp. This is an easy calculation. So this is what we have. We have two types of solutions. We have a uniform streaming solution at a constant velocity v in the y direction, and we've got this non-trivial solution that scales like r to the 3/2 times some very specific angular dependence. So from this stream function, I can work out what's the x and the y component of the velocity field. Here it is. So taking one derivative, the velocity field goes like y to the 1/2. Now the free surface must be a streamline of the flow, which means that dH dy must be ux divided by uy, which is y 1/2. And if I integrate once more indeed, finally I get h equals y to the 3/2. So by a rather more involved process, I actually do find the characteristic exponent for a cusp which was found earlier without having invoked any particular geometrical insight, but rather by a direct attack of the equations of motion. The one thing I have not taken into account, and which is important and will be addressed later, is the fact that the solution I have here is very singular at the tip. In particular, if I have surface tension, which I've not spoken about, I would expect this tip to be rounded. So to investigate this further, let's go back to a possible geometrical description. But to have a first glimpse of why a geometrical interpretation might be in order, let's go to the beautiful solution found by Jong and Moffat in 92, which looks at a particular flow situation exhibiting such a cusp. So they take a large bath of viscous liquid, solving Stokes' equation inside the bath. Underneath the free surface at a fixed distance, they have a dipole of vortices, which experimentally would be two counter-rotating cylinders. And they find that the free surface is deformed into a sharp cusp if the driving is strong enough. But in fact, they find that the cusp tip is not of zero size. So that's different from what you see in the optical manifestations. They find that the cusp tip actually remains rounded, but with a radius of curvature which is exponentially small in the capillary number, where the capillary number is a characteristic of velocity of the flow. And they do that in an ingenious way, which will allow us to link back to a geometrical interpretation. Namely, they map the flow domain from a disk into the domain such that then the radius here, the circle here, maps onto the free surface. And for our purposes, it suffices to say that they find a holomorphic mapping Z from this disk here onto the flow domain, which means that if I parameterize the surface here only, Z of theta is a smooth function. So I have here really two equations, x of theta and y of theta, which is a smooth function containing a single parameter, which is the strength of the driving. And what I'm looking for is a situation, these two curves still being smooth, but where I get a singularity of the surface shape. And the only way this can happen is the case that this mapping here no longer has full rank. In other words, that Z prime, that the curve becomes non-invertible. That means that x prime of theta and y prime of theta, both derivatives at some point, which I call 0 here, is 0. So to understand the geometrical underpinning, what we have to do is we have to take an arbitrary smooth curve and investigate properties of this curve near such a point where both derivatives vanish. How does it look like? And it turns out this will be a generic shape determined by geometry alone. But just like I looked at the fold. It's very revealing to interpret this geometrically. So again, let's take a piece of string or some, imagine some piece of string. So this curve is smooth everywhere. It's non-intersecting. And now imagine I deform this this wire, let's say a wire, in a smooth fashion, such that eventually, as the wire is sufficiently deformed, it self-intersects. So in particular, at this point here, the original mapping is no longer invertible. And so it's geometrically almost obvious that just like in the example for the fold, there must be a critical state where I'm just going from non-intersecting to intersecting, where there is something special, and this is what it is. You find an exact cusp at the point where I go from one geometrical state to the other. And let me briefly sketch how this is just like in the case of the fold. This can be understood by a simple argument of local deformation. In general, a curve will be given like that. Locally, that's the most that's the general description of a smooth line locally near a point x0, y0. It is clear and that by rotating this object, I can bring it into the standard form x just being proportional to phi and y equal 0. That would be a line parallel to the x axis. And the non-invertible state would correspond to A1 being 0. So if A1 is 0, then of course nothing is left here, which simply means that I have to press on and add corrections, higher order terms. So that's what I'm doing. The critical point of this mapping would be A1 equals 0, which I now call epsilon. And so here I have x equals epsilon phi. And now I have to, just as I did for the fold, I'm taking into account powers of higher order in phi. Why do I not stop at phi squared? Well, I'm not stopping at phi squared because for epsilon equals 0, because y also goes like phi squared, this would simply be a straight line. So I have to, in fact, continue to the third order in phi. And by a simple transformation, again, shifting the value of phi, I can eliminate this quadratic term, and I end up with the normal form for a cusp, a universal description, which is x equals epsilon phi plus phi cubed and y going like phi squared. So epsilon greater than 0 corresponds to this situation. Epsilon where the cusp tip is rounded on some scale given by epsilon. At epsilon equals 0, I have a perfect cusp, and for epsilon negative, I have a self-intersection. And let me point out that I can write this shape in a similarity form, where capital X and Y gives me a parameterized version of a similarity function. Two different functions, one for epsilon negative before the singularity, one valid after the singularity. And here again, in the scaling, you see that the typical width of this solution is epsilon to the 3/2. Here is again our characteristic exponent, which reappears in the similarity description. And so it is clear from Moffat's solution that if there is a singularity like that in Moffat's solution, it must be of this form, because the only thing I've made use of here is that the mappings are smooth, and that's guaranteed by the method of solution of Zhong and Moffat. Except that the solution of Zhong and Moffat only pertains to a particular geometry, and I would like to know whether I can extract this structure just by looking at the local behavior of the Stokes equation, whereas Zhong and Moffat's analysis directly goes to the complete global problem. And here it gets slightly more technical, but I find also revealing. I try to find this local solution using what's known as the boundary integral method, which has mostly been used for numerical purposes, but which I use to gain analytical insight into this class of solutions of Stokes' equation. So to formulate the problem very carefully, this is what I'm interested in. I have a cusp shape here, and by what I've said before, I will pretend I know what the shape of this surface is, and then see whether I can find the corresponding flow solution, which is indeed consistent with the shape of the surface. In the interior of my near cusp, I have an inert gas. In the outside, I'm solving Stokes' equation. So equations of fluid motion dominated by viscosity. I have the usual boundary condition here on the surface, namely the normal dotted into the stress tensor is the surface tension coefficient times the curvature times the normal. So this is my flow problem. And to fix the shape of the free surface, I also want that the free surface is a streamline, so I want that the velocity dotted into n is 0. So the velocity is always parallel to this free surface. And I'm solving this problem using the boundary integral description. Here are the equations in units of a characteristic velocity, which is gamma surface tension over the viscosity. The essence of the boundary integral method is easily understood. The flow in such a free surface flow can be understood as being driven by the surface tension, and I can think of this surface tension forcing as a distribution of delta functions along the free surface whose strength is proportional to the curvature and pointing in the direction of n. So if I manage to find a solution to Stokes' equation pertaining to such a delta forcing, I simply have to add up over all of these delta forces and I get the complete flow solution. And that's what I've done here. That's this first integral. So the velocity that's generated by such a directed delta forcing is given by this expression J here. This is known as a Stokeslets. And if I add up over all of these Stokeslets, I get the complete velocity at a point along the surface, which I parameterize by psi. So psi1 is where I'm looking, that's where I want to know where the velocity is, and psi2 is what I'm integrating over. This would be the true description if there was only one phase. But here there's a jump of viscosity across the interface because the gas is assumed as having zero viscosity. And to correct for that, I have, unfortunately, the second integral, which contains the velocity itself. And this is then some external driving, which I imagine drives the problem from afar. And this notation here, n hat, is simply the normal vector, but not normalized, but simply given by this expression, which has the advantage that in this boundary integral description I can use any parameter to a parameterized free surface. So now this is what we're up against. This is what we have to solve. And the insight I'm using to make this feasible is the fact that I pretend I already know what this free surface is, because we just on the previous slide, we worked out what a generic cusp should look like. Whereas this is normally the difficult part, to work out what the free surface shape is. But in this case, I know what it is. So why is this problem not completely trivial? So the most natural assumption is that I use the similarity description. So my first impulse was to take the similarity description of the cusp, insert it into the boundary integral equations, and hope to find a description in terms of the similarity variable sigma alone. But this doesn't work. And this is seen very easily if you take this description here and compute the curvature to leading order as epsilon goes to 0, you see that you get a description which is very singular at the tip, which is very singular, goes to infinity as sigma goes to 0. So this doesn't work, and the reason is simple. The reason is that indeed this scaling here only pertains to the cusp region here. It cannot work here near the tip. So instead, from this insight, I see that I need a different scaling region. Namely, I need a tip region where x is comparable to y, and I can realize that by reparameterizing sigma in terms of a new variable psi. And if I do that, I get a new parameterization where now automatically x and y are of the same order in epsilon, and this cusp exponent, this higher order term, is of lower order in epsilon. And then indeed the curvature becomes nice and regular as a function of psi, as expected. And so what I do now is use this parameterization in the boundary integral description. That means I have here an inner part of the solution, I have a cusp region, and I have a far field which is non-universal, and it was given by the particulars of the flow. So now what I do is I insert these scalings into the boundary integral description. What's left to do, of course, is to know what the velocity is, what the tangential velocity is along the free surface, because that's needed for the boundary integral description. And here, to find this, I could somehow guess what the answer is, but what I in fact did was work back from the exact solution Zhong and Moffat have found and evaluated the asymptotics of epsilon going to 0 at constant parameter psi, where psi of order 1 corresponds to the tip region. And you end up with a surprisingly simple answer. So this is the leading order expression for small epsilon of the tangential velocity along this line. And so now I'm coming back here again, is my boundary integral description. I have to plug all of these expressions here into the boundary integral formulation. And just to give you a flavor, let's first evaluate the left-hand side. The left-hand side is, of course, easy. The left-hand side is this tangential velocity times the tangent vector. Into leading order, this is the tangent vector. And now comes the hard bit. I have to evaluate these integrals, but now these are all known expressions in principle, and I can evaluate these integrals. And just to give you a flavor, this is what it is. This is the integral, and the integrand is this expression. And what I have to do here is I have to integrate over psi2, and I have to verify that the sum of these integrals indeed equals the left-hand side for any psi1. And this is something that can indeed be done. Strictly speaking, it's not really necessary. It's clear that it has to work out like that because I've shown that this equation is closed at leading order at the tip. So the existence of the local part of the Jong-and-Moffat solution already guarantees that this must work. And you can work that out and verify that it solves this equation. This is the x component. You can do the same thing for the y component. The only wrinkle is that in the y component, there are some unknown constants of integration, which come from the fact that these constants are not closed near the tip, but some of the contributions to these constants come from the outer region of this solution, which you have to evaluate as well. And the interpretation of this is that if I write the curvature as a function of the capillary number, that is a typical velocity generated at the tip, I get a non-universal relationship which depends on the details of my flow problem. And you see this from this equation and the fact that this aspect of the equation is not closed at the level of the tip. So now this is the tip region. Now I have to verify that the solution is also true in the cusp region. The cusp region means that now I have to hold the parameter sigma constant as epsilon goes to 0. I repeat essentially the same analysis as before. To leading order in epsilon, the velocity is now given by this expression, and I have to do the integral. It turns out that the leading order contribution to the J integral, even here in this cusp region, comes from the tip region. The reason being that this is a very strong, almost delta-like forcing near the tip. And so using this insight, I can work out the J integral explicitly by integrating over the tip region. And so I still have to do the K integral. The K integral is of a slightly different nature, and indeed its physical properties, its physical meaning is different. It turns out that the leading order contribution to the K integral in the cusp region comes from a local region around the reference point. And the trick here turned out to be to rewrite the integrand in terms of this Lorentzian. This is the structure indeed the solution had. All of these coefficients here I can calculate in an expansion in epsilon, and then this integral is very easy to do, and I get these expressions for the integrals, and you can verify that again to leading order in epsilon. This gives an exact solution to the boundary integral equations. So thus I have shown that the cusp shape, rounded cusp shape, whose shape came from geometrical insight, is indeed an exact solution to the Stokes equation to leading order in epsilon. And as an additional insight, there's the interesting observation that this tip region is actually a closed solution in its own right. So if I have a tip like that appears in a different context, for example, when I have the coalescence of two drops, I've shown implicitly that the tip region in the coalescence of two drops also must be of the same shape as I've described here. So this, the conclusion is that this solves the integral equation. Remember, in the integral, the cusp had this free parameter C, and this is indeed a free parameter of the solution, and and you can verify that the integral equation is verified for any C. So, among others, this method gives you exactly what are the degrees of freedom of your solution. And that brings me to the end. I can conclude that these rounded cusps are a generic feature of Stokes flow. In particular, the rounded end is a subregion that has a closed form solution in its own right, which is something I found surprising. There is, I've discovered, through a friendly referee, that there is an alternative approach which has been developed to some degree by the Oxford people, although not applied directly to this problem I've addressed here, but rather mainly to the problem of coalescence of two viscous drops by Howison and Sam Howison and John Ockenden. The approach I've given here, which doesn't use an exact flow solution, has the advantage that it can be generalized. For example, one can imagine that the flow is not perfectly two-dimensional, but I allow the flow strength to vary in the third direction with corresponding slow variation of the curvature, and then such a asymptotic approach could be generalized to such a situation. However, although I started with geometry and a simple derivation of the cusp from geometrical means, I must say, going through the technicalities of my calculation I've shown you today, it's still not absolutely clear to me how the geometry is really linked to the intricacies of the Stokes equation to yield these beautiful cusp solutions. And that's all I wanted to tell you today.
Okay, thank you very much. Thank you, Jens. Wonderful talk. And I wonder if any of our people attending online and directly your lecture has questions. But I have actually one question, and maybe I'm not sure if it makes any sense, so please forgive me for this. But I wonder, can we, is there any interest, or probably does make any sense to relate viscosity, fluid viscosity effect to the extent of validity of the inner region and the cusp region? To what extent the viscosity influences the validity of the analysis on the inner region? I imagine that the two regions match at some distance, let's say, from the tip. And I wonder if there is any information.
But I have the feeling that this already scaled out. I mean, I'm already in the limit of, Stokes flow. So, and, in the calculation, the viscosity goes into the characteristic scale of the velocity. So everything is written in terms of gamma over eta, which includes the viscosity. So it sets the velocity scale, right? But it doesn't affect the geometry. I mean,
I understand.
If small inertial effects would come into play, that, of course, that would be, and then that would be different. And it's actually an interesting question whether there's anything you could still do with this geometrical means if you jettison the assumption of zero Reynolds number, or maybe this is a way to understand where this geometrical interpretation really comes from.
Maybe Keith wanted to say something.
Yeah, if I comment on that, surely the answer, Jens, is that viscosity does enter into the capillary number definition of capillary number as well.
Sure.
And the radius of curvature at the tip depends very critically on exponentially, in fact, on the capillary number. So the answer to Renzo's question is yes, viscosity does have a very important effect in conjunction with surface tension.
Yeah.
I mean, it's the ratio of these two that matters. I think. Is that not right, Jens?
No, absolutely. I agree. Yeah. It's just
I should add that for me, it's always nice to be reminded of that period when I worked with Jaitak Jong on this problem back in the early 1990s. And I think we always believed that this cusp form and the solution we found that although it was, as you say, for very particular geometry, in other words, a vortex dipole below the surface and an infinite extent of fluid, we believed that the cusp shape would be universal. And in fact, the experiment we did involved two cylinders rotating, and we could vary the radius of the cylinders and their separation and so on. So it wasn't a very good vortex dipole, but nevertheless, it formed the same sort of cusp whenever these cylinders were rotating rapidly enough.
Yes.
Which made us believe that, yes, this was. And then you mentioned Reynardi with Dan Joseph. They'd published a paper just the year before, which was a single cylinder, partially submerged, rotating rapidly. And it drags fluid down again and forms a cusp. And again, I believe that must have the same. Well, you've proved that when a cusp forms, and that's the beautiful thing about yours.
I completely agree. And of course, I didn't expect anything else. Indeed, I would rather say the insight I got from my calculation is rather an insight into these different scaling regions you need to actually understand the balance. That was a surprise.
Yeah, that is beautiful. It's very beautiful
to me. So to me, that is the actual interesting bit.
It's brilliant that you can do that in this way and by purely, really local considerations. And of course, what was important in these early days is that you then went on to resolve the singularity by allowing for the entrainment of air through the cusp, which is, as you pointed out at the beginning, the manner in which bubbles of air can be entrained into a fluid. And that really is important in chemical engineering context.
Yeah.
And I think also, even in, I mean, it should be possible to do this at high Reynolds number as well, because I think it's the same, it is the same sort of mechanism. If you have a tap pouring water into a bath of water, so this is high Reynolds number, at a fairly gentle rate, it forms a circular cusp, which is rather gentle, nothing very dramatic. But of course, if you increase the speed of the flow by turning up the speed of the tap, as it were, then bubbles form.
Yeah.
And that's because somehow the bubbles of air are entrained through this cusp region. That's what I believe, anyway. That's what I've always stated.
I'm committed to addressing this problem properly, but if at one point. But if you estimate the capillary number, you actually get you will know that the capillary velocity of water is exceptionally high, and so if you take an actual situation involving water, the capillary number is always very small. So I believe it cannot simply be the same viscous mechanism.
Right.
Must be.
Well, it'd be wonderful to solve that problem.
Yes. Yes.
But thank you very much, Jens, for a beautiful talk. Lovely.
Thank you.
I understand my own theory better now.
I believe we have to leave Jens to lecturing now. And
that's right.
So thank you. Thank you very much, Jens. Wonderful talk. Thank you. Thank you very much.
Okay. It was a pleasure.